Hello and welcome to this coding interview preparation course. This course will help prepare you for the unique and challenging aspects of a potential coding interview, including some of the approaches to problem solving and computer science foundations that you may need to be aware of or apply. Let's take a moment to preview some of the key concepts and skills that you'll learn. In the first module, you'll start by discovering what a coding interview is, what it can consist of, and the types of coding interviews that you might encounter. You'll also explore how you can prepare yourself for a coding interview, including a focus on communication, such as explaining your thought process, handling mistakes, and the STAR method. You'll also learn about how to work with pseudocode to demonstrate how you might reach a solution, some important tips that might help with any practical solution design, and how to test your solutions. Next, you'll get an introduction to computer science, starting with the fundamental concepts of binary, and how binary relates to real-life hardware and computing. You will explore memory and the key components of computer memory, read access memory, RAM, and read-only memory, ROM, and how your computer uses memory to perform its tasks, processes information, and store data. Next, you will take a dive into time complexity and the key concept that underpins this, Big O notation. And you will discover some of the types of Big O notation and how this applies to algorithmic processing. You will explore space complexity, which is essentially the space required to compute a result. In the second module, you will learn about data structures and how each one comes with certain benefits and limitations. So understanding each of these can be really important when designing a solution. You will start with basic data structures by addressing the implementation and capabilities of data structures between various programming languages and the similar patterns of the overarching architecture. You will explore the main basic data structures, strings, integers, booleans, arrays, and objects. You will go on to examine some collection data structures, starting with lists and sets. Then you will learn about stacks, queues, and trees, before moving on to some advanced data structures, namely hash tables, heaps, and graphs. In the third module, you will get an introduction to algorithms, including the types of algorithms available to you and how best to work with them to sort and search your data. You will start by exploring sorting algorithms and how working with sorted data or having the ability to sort your own data can result in significant time savings. And you will explore the three main types of sorting: selection sort, insertion sort, and quick sort. And you will learn that each approach has its trade-offs and is more effective in some environments than others. Next, you will discover searching algorithms and how each type provides its own framework for problem solving. You will also gain insight into time and space complexity in both searching and sorting algorithms. You will take a deep dive into the processes and underlying mechanisms involved with divide and conquer, recursion, dynamic programming, and greedy algorithms. Finally, in the last module, you will get the chance to recap on everything you've learned throughout the course before taking the graded course quiz, which will test you on all of the key concepts and skills you have learned throughout the course. In this video, you have had a broad overview of the course. Specifically, you have discovered how this course will help you prepare for the unique and challenging aspects of a potential coding interview, including some of the approaches to problem solving and computer science foundations that you may need to be aware of or apply. Now, let's get started.
It takes approximately 39 months to find software engineers and developers in tech hub cities in the US.
The interviews that you will go through sometimes have skills that you don't normally use in your day-to-day job.
It's not just about how well you can program, it's also about how well you're displaying a lot of interpersonal skills, how well you're able to drive projects, how well you're able to collaborate with others.
You don't need to worry about showing up in a suit. You really can just kind of wear whatever, be yourself, and focus on the technical aspects of the interview. Hi, my name is Julie, and I am a software engineer on the IG shopping team at Meta New York.
Hi, my name is Moxie Herrera. I use they, them pronouns. I'm a software engineer in the social impact org at Meta, and I work out of the Menlo Park office.
My name is Chanel Johnson. I work remotely in Maryland for Meta, and I'm a software engineer for the Facebook App Core Architecture team, where we work on infrastructure for the Facebook mobile app.
My name is Mari Batulando. I am a software engineer for the Web3 monetization team within Meta, and I work on different ways creators and influencers can make a living off of the Facebook platform using Web3 technologies like NFTs and cryptocurrency.
I think it can be broken up into three general areas. One is the application process, one is actual interviewing, and one is the calibration process when they discuss your packet and give you an offer. In terms of the actual interview process, it's broken up into technical, architecture, and behavioral. For the application phase, it's recruiters kind of screening your resume, your work experience.
The recruiter then will meet with you and talk with you more to get a better idea about your skills, your experiences, what you're looking for to make sure that you're a good fit for the role.
Phase 2 is the technical aspect of it. There can be a range of 1 to 4 or 5 or even more interviews there.
So this could be things like a coder pad interview where you're on the phone or over a voice chat with a recruiter or a engineer to kind of go through some technical challenges. You'll have some behavioral interviews where people are just kind of engaging of what it's like to work with you, how do you solve problems.
And then oftentimes there are architecture interviews as well, where you build kind of an end-to-end product, discuss the full architecture for that. Phase 3, the final phase, is when everyone involved in the process kind of gets together and discusses how you did throughout the phases and if they should extend an offer to you.
If you decide to take on the offer, you go through what is called boot camp, a process where you get to learn the ropes of how it is working at Meta, and also sit with the teams that you're interested in so that you know what choice you end up making, and you get to choose ultimately what team you go in. If you are interviewing for a specific pipeline like iOS, Android, or ML or AI, you should expect some questions that deal with that specific domain. So for example, in my case, I was interviewing for the iOS pipeline. So in addition to those algorithms and data structure questions that I got asked, I also got asked some iOS questions or some questions that I deal with in my day-to-day work as an iOS engineer. So you can imagine similar things as if you were an Android engineer or if you were an AI or ML engineer.
I think in the application phase is when a lot of candidates get screened out. What can really help there is crafting your resume and focusing on real experience that will really help when it comes to software engineering roles. So if you don't have job experience, totally fine, work on side projects. And that will show both, concrete experience and a drive that you're actually interested in working on the role that you're applying for.
I would say the coding interview portion is where a lot of people get disqualified. There can be many reasons for it, but the biggest reason I see is that sometimes when you're writing out your code, the person being interviewed is not explaining their thought process, what's going on. They're not asking clarifying questions. Sometimes if the interviewer gives them a hint, they're not listening. So communication skills is where I also see a lot of people getting disqualified in the coding interview portion.
Some candidates I see do not have a structured process for answering problems they may not have heard or seen before. And they kind of just go cowboy coding and just start coding without even knowing what they're supposed to solve. So I think having a robust problem-solving process for questions you may or may not have seen before is very important in doing well in these coding interviews.
One common problem is people get stuck and they get so wrapped up in it that they're unable to kind of take feedback. What interviewers are looking for are a holistic approach to the problem. So it's not just about solving the problem, it's about how you go about it. It's about collaboration with the interviewer. So that's a really important piece to remember.
The biggest thing that I've learned is to really be myself. I have found it much more successful and way less stressful to just be who I am unapologetically. But it also means whenever I come come forward as like a candidate, like I am presenting myself as I am and not trying to hide anything, given that this is who I want to be at work. This is who I want to be in my life. And I think having that mentality has made it so much easier, regardless of the outcome of the process.
Think really hard about what you want and choose companies that resonate with what you value. There are other things other than compensation and just the prestige of a company that matters in how happy you are with the company. So make sure you make a list of those and consider that whenever you are choosing companies.
My biggest piece of advice is just going through as much practice as possible. So, two main ways to do that, I think, is one, while you go through lead code problems or mock interviewing, doing the whole thing end to end. Even if you're unable to solve the problem, you get stuck, you don't know what to do, finishing it out as if it's a real interview, it'll give you really good practice for when you actually get to the interview. And then the second thing is apply to as many places as possible. It gives you the best chance of getting interviews. And then once you're in a real life interview situation, it's a lot easier if you've already had experience doing that before. It really helps calm the nerves and it helps you get more practice in.
There's not all just only like one particular person that we're looking for when it comes to tech. We want different backgrounds and different perspectives and experiences because that's the only way we're going to make our products better. We need that. It's such a rewarding process to make an impact and actually for the better, and just meet with people and keep learning. You will never get bored at this job, never.
As you start to interview, you will face many ups and downs. And these are all experiences you can learn from. If you keep pushing, keep learning, you will eventually get to a role where you can start an amazing career in technology.
The amount of preparation you're going to do is going to lead you to having a really big impact in the world because software is just everywhere and it's used by millions and billions of people. So I think it's well worth the preparation, the amount of effort it takes to land a job at a very influential and impactful tech company.
A technical interview is where you demonstrate your competency to code. Normally, you would have completed a screening call and demonstrated that your soft skills are suitable for the company. Soft skills relate to your ability to conduct yourself socially. This includes communicating clearly, having a good work ethic, and that your presentation aligns with the company values. The technical interview is to determine that you are technically capable of the responsibilities of the role. In this video, you will learn how to approach the technical interview. When going for a coding interview, it will help you to keep the following steps in mind. Prepare to succeed. Solve the problem conceptually first. Employ appropriate tools. And lastly, optimize the solution. Doing a deep dive into these concepts will help you understand how to apply the method. Firstly, prepare to succeed. Many candidates might feel some trepidation at doing a technical interview. What happens if a question is asked and my mind blanks? Fortunately, there are steps that you can take to prepare for success. Failing to prepare is preparing to fail. Solve the problem conceptually first. Before employing a solution, it is a good idea to first have a clear picture of the question and what the answer will look like. Take some time to ensure that you are clear on what is being asked. An interviewer will have no issue with you seeking clarification from the onset. If there is a whiteboard, then use it. Jot down the major points of the problem before outlining a potential solution. Here is an excellent opportunity to show your ability to reason a problem using pseudocode before writing a single line of code. Demonstrating your ability to reason out a problem is halfway to it. Remember, one can always be taught to code. An ability for problem solving is a much sought after ability. Be vocal as you assess the problem and show the interviewers how you engage with problem solving and why you elected one approach over another. It can be a big help if you can equate the problem with one you already know. Later in the course, there is a video on the practice of divide and conquer. This is a good opportunity to employ that. Breaking the problem into smaller ones can help to solve a seemingly complex problem. If there is an additional time constraint and you exceed the allowed time, you will still be able to show functional chunks of code. Employ appropriate tools. The types of problems presented in a coding interview will have to be completed during the interview time. Thus, the solutions will not be excessively complicated in nature. They are designed to test your problem-solving ability on a microcosmic level and your awareness of the available tools. Consider the classical count the socks problem. You are given an array that represents sock colours. Yellow socks are represented by 1, blue socks by 2, red socks by 3, green socks by 4, and lastly orange socks by 5. Sock colours equal the numbers as explained, namely 1, 2, 2, 1, 1, 3, 5, 1, 4, and 4. Determine how many pairs of the same colour socks exist. So, there are 4 ones, which equates to 2 pairs of yellow socks. 3 and 5 represent odd socks. Although it is a red and an orange sock, they don't have matching socks to form pairs. There are 2 2s and 2 4s, which each represent a pair of blue and green socks. To solve this problem succinctly, you can utilise an appropriate data structure. Later in this course, you will review data structures. One video outlines how a dictionary stores key value pairs. A solution would be to use the sock colours as keys and the count as values. Then, iterate over the dictionary and retrieve all odd numbers, which indicates the presence of any odd socks. While there are many programmatic ways of solving this, the use of existing structures minimises the code required and demonstrates familiarity with fundamental building blocks. When possible, always utilise existing approaches rather than attempting to implement manual solutions. In addition to familiarising yourself with staple structures, review common sorting and searching algorithms before engaging in any technical interviews. It is good practice to optimise your code. That means writing or rewriting code so a program uses the least possible memory or disk space and minimises CPU time or network bandwidth. Coding the solution is a good step towards a respectable solution. Ensure you make time to optimise your code. Another concept you will meet in this course is time and space complexity. Can you demonstrate to the interviewer that you understand these crucial concepts? Put simply, it is a way of measuring how fast and how much space your solution will take. When presenting your answer, outline your solution's time and space complexity, and then see if you can improve. Identify any repeat or overlapping code. Demonstrate that you can modularize this code into a function that is callable repeatedly and reuse code when possible. An often repeated principle for good programming is dry. Don't repeat yourself. It is the idea to only say a thing once in code and reuse as often as needed. Additionally, if there are portions of your code that are no longer required as a result of modularizing or as a result of an avenue of thought that was not completed, remove it. Avoid excessive compiler calls. If you are searching for a value in an array, terminate the loop when the item is found. A very achievable optimization on your code is to include a return statement when a value is found, or to use a loop that is dependent on a Boolean. As soon as a result is found, the loop can be terminated. This increases overall efficiency and reduces time complexity. Space complexity is all about being clever with memory usage. Whenever you can, avoid creating more variables than needed. In this video, you learned about some approaches that can be used regardless of the challenge presented. Even if you're not familiar with the problem or don't achieve a result in the time allotted, always strive to demonstrate your reasoning and best practice approaches. Prepare for technical interviews by doing practice solutions to online problems and, when possible, employ a similar methodology to each challenge so that regardless of the challenge faced, you are working from a comfortable framework. A coding interview can appear like a daunting task. There will always be elements of the unknown involved, and your desire to succeed may add some pre-interview nerves. Just stay calm and think logically. Good luck. The success of an interview is almost fully dependent on how you communicate with the interviewers. You wish to convey your suitability, and the company would like to find a candidate that is appropriate for the role. In this video, you will learn about verbal and physical or non-verbal communication. Never underestimate the power of first impressions. It is important that every interaction with you as a potential employee reflects the capabilities that you will bring to the organisation. The first non-verbal sign that you can show is punctuality. It is good practice to arrive at least 10 minutes before the scheduled meeting is supposed to start, particularly if you are unsure of the specific venue where the interview will be conducted. It takes time to navigate a building, and you wish to appear composed and ready for the interview, not out of breath and flustered. Over the course of the interview, ensure that you maintain eye contact and actively listen to the questions that are being asked. Dress appropriately for the meeting. Generally, a job interview calls for you to wear professional or business attire. Make sure your clothes are clean and neat. That shows respect and reflects positively on yourself. Finally, maintain a good posture and refrain from squirming and needlessly touching the face or wringing the hands. While being nervous about and during a meeting is understandable, these gestures may unintentionally convey a sense that you don't feel up for the task. A great way to settle the nerves is to have done your due diligence prior to the meeting. Make sure you understand what the job entails and what the company does and stands for. Although it is important to understand the importance of non-verbal communication, verbal communication is equally important. You need to be able to speak to your interviewers. A good indicator of how to conduct yourself in an interview is to observe the interviewers. Listen carefully. They will lead with questions to see if you fit the required skills and personality profile. Typically, an interviewer will aim for the 80-20 rule, speaking for 20% of the time and allowing you to present yourself for the other 80%. So, allow the interviewer to direct the question to you completely before answering. Use clear and concise language in your answers. The temptation, particularly if you have done diligent preparation, is to try and respond to a question with everything you know on the topic. This may lead to some rambling. A better answer is one that stays on topic and allows for the opportunity for further questions. A good interviewer will follow up with related questions, so this allows for the conversation to flow. Refrain from exaggerating your abilities or being negative towards yourself. Be careful not to use emotive terms that can convey negative attitudes about yourself. For example, rather than saying, "I failed at that task," you could say, "That task was challenging, but provided me with some ideas for future areas of research to explore." Additionally, avoid excessive slang, cursing, or inappropriate humour. A good methodology to follow when conducting an interview is the STAR method. Initially, the interviewer will attempt to make you feel welcome by giving you an opportunity to talk about yourself. What is on your CV? What do you know about the company or the role? As the interview progresses, the discussion will focus more on your abilities and suitability for the role. It is important that you can convey why you are a good fit. Typically, questions will focus on the business needs, either technologies that are being used or problems that have had to be overcome. The interviewer wants to know how you would respond to issues that arise when engaged with the job. Therefore, try to answer questions using the STAR method. Include the following 4 points when answering a question: the situation, the task, the action, and lastly, the result. Here are some examples to demonstrate the method more clearly. What is the context of the situation? What is the project? And what are the challenges faced? Looking at the task, what would your responsibilities and assignments be? What actions will you take to rectify or address the challenges? What are the results or outcomes of your actions? How did taking this approach impact the result? Using this approach as a template for an answer will give depth to your responses. It provides a workable framework for an answer. It also gives the interviewer a chance to respond with more related questions on areas you feel comfortable discussing. Let's recap what you have learned in this video. An interviewer will be on the lookout for candidates that can clearly convey a concept. Your first task is to communicate why you are suitable for the role. This is done verbally and non-verbally. Finally, the STAR method is a very efficient framework for engaging with technical questions that will arise over the course of an interview. In this video, you have learned that verbal and non-verbal communication is key during an interview. In any given role in a company, you may have to deal with the stakeholders, whether it be complications with the role or why a given solution is the optimal path to take. So, take what you have learned about communication and apply the principles with confidence.
Almost half of software developers, according to data from a popular employment website, find the coding interview portion the most stressful portion out of all of the technical interview.
You are going to be asked a lot of technical problems, a lot of architectural problems, organizational problems. They really want to know who you are as a person and what you value.
When I was interviewing, one way that I practiced was I had an actual stuffed animal that I would talk to. And this just really forced me to practice the interview end to end, as if I was actually talking out loud.
I think the interviewers at Meta have been trained very well to make the interviewee feel welcome and comfortable in solving problems together. My name is Mari Batulando. I am a software engineer at Meta, and I work in the FB Web3 monetization team, where I help creators and influencers make a living by using the Facebook product.
My name is Moxie Herrera. I use they, them pronouns. I'm a software engineer in the social impact org at Meta, and I work out of the Menlo Park office.
Hi, I'm Julie. I'm a software engineer on the IG shopping team at Meta New York.
My name is Chanel Johnson. I work remotely in Maryland for Meta, and I'm a software engineer for the Facebook App Core Architecture team, where we work on infrastructure for the Facebook mobile app.
There are generally 3 different types of interviews: technical, which is your regular elite code interviews, architecture interviews, and then behavioral. The technical interviews, the elite code-esque questions, you'll typically have 2 to 4 of these in the interview process. 1 or 2 will be as a screen, and then there'll be a couple more after you pass the initial screen. And these are just going to be 20 or 30 minutes per question, just your classic leak code questions. The architecture interview is going to be about a 45-minute to hour-long interview where you'll get a question of how to build kind of an end-to-end feature. So this can either be more product-oriented, like build Tetris, or it can be more back-end oriented, kind of focused on how data flows and how to scale this to many users. And then finally, for the behavioral interviews, you can expect questions like about your experience working with other people, collaborating, challenges you've faced, exciting projects that you've worked on.
Questions I usually ask is, what is an experience that you've had when working on a team that things did not go well? And the main reason I ask for this is because at Meta, you're going to have to be working with a lot of people. It's not just a solitary job. So you need to learn how to communicate and how to really learn and grow with people.
When I was interviewing, I was asked a lot of general questions that I would expect as an iOS engineer. So for example, how would I build the newsfeed surface in the Facebook app? You know, what objects will I make? How will those objects talk to each other? What networking APIs do I expect? And being able to, at a high level, describe how I would tackle these challenges and how I would structure the app as an iOS engineer. So that's a very classic question.
One advice I would give in order to practice for interview questions is to talk out your solution when you're whiteboarding it. So one thing I would do is like with friends or colleagues, when you write out your solution, explain your thought process on what's going on. Are you considering time complexity? Are you considering how to make this faster? How to reduce space? These are things that we also want to see as interviewers because when you're coding on the job, these are things you need to think about. So this is a good practice for you to explain when you go through your code of like, hey, this is why I'm doing this because of X, Y, and Z, and I'm also considering this.
As an interviewer, I am actually rooting for you to do well because what I want as an interviewer is to not sit there and stare at the screen for 45 minutes watching you struggle. I would much rather see you succeed and for us to work together on a problem so that I can gather as much signal from you as I can so that I can make a good decision whether or not you would be a fit for Meta.
In terms of dress for the interview, the key is to really just be yourself. Wear something that you're comfortable with. No one expects you to show up in a suit. I get a lot of interviewees that are wearing just a t-shirt and jeans.
I am really looking for a candidate that is willing to explain their thinking, willing to engage very deeply, and show a high level of confidence and knowledge.
So the most common mistake I see people making is they might be a really talented iOS engineer, but their software general skills might be lacking. So make sure you're preparing for those general algorithms and data structure types of questions because they will come up when you are interviewing, regardless of the pipeline that you're interviewing for.
Sometimes in the technical challenge, you'll get stuck. And the worst thing you can do is say nothing, because I can't read your mind and I don't know what you're doing. So you really want to explain what you're thinking for, how you're stuck, why you're stuck, because even if you don't get the answer right, if you can show that you have a good understanding of the problem, that can be enough to get you to the next round.
What really impresses me about candidates is when they come prepared for the interview. And you should obviously come prepared to the interview, but when they've done their research on the company, they know the values and they know how they apply to their values and what they can bring to Meta.
What really impresses me about a candidate during an interview is when they can take feedback from me. So even if they are on the right track already, sometimes if I can see that and push them a little bit more, that's a really good sign that they can hear my feedback and work with me to solve whatever problem is at hand. It gives a good indication that it's someone that I would want to work with in real life.
Interviewing is really about showing who you are. It's really about, showing what you know, how you grow, how you learn. And there's not a single trick to it. You really have to kind of figure out a little bit about yourself and how you display these things and make it work for you. A candidate that's very enthusiastic, excited to be there, and has a really positive demeanor. That just really shows that that's someone I want to work with, someone that's going to be passionate about the work they do. And that is what I think leads to success, is that passion.
On the other side of the interviews, even though it can be a really long process, it is really rewarding to start to actually work on the products that people use every day. At a place like Meta where things scale so large, it's really cool to see one of the features you build being used by millions of users.
And you get to work with the smartest people I've ever met in my life. And that will help you grow as an engineer. And you would be shocked at how much you will learn and grow within a short time here.
Thanks for watching. Hope that you were able to learn some good tips at interviewing at Meta, and good luck on the rest of your journey.
In this video, you will learn about binary numbers, what they are, and how computers use them to represent human language. You will learn how positional encoding can turn a limited set of numbers into an infinity-sized representation of values. Lastly, you will learn how computing the power of a number can be applied to determine how many states this simple representation can hold. Traditionally, you count using 10 different digits, 0 to 9. This stems from the early development of maths. It was a natural progression resulting from humans having 10 fingers and 10 toes. counting with the use of 10 digits is referred to as base 10. Base 10 means you have 10 different numbers to use before you have to add another digit and reuse numbers. Each time you exhaust the range, you reset the number on the left and add a 0 to the right. This new digit has to be 10 times greater than the digit to its right. The number on the right is the reset, and the count begins again. The use of the position of the number to denote a progressive increase in value is called positional notation. When you consider it, it is an early implementation of an algorithm to allow for the recording of an infinite number of values. Simple in implementation, but very powerful in effect. Binary works using the same positional notation approach. It is another common counting approach that employs base 2. This means that all of the values are represented with either a 1 or a 0. Computers store information as bytes. Each byte is made up of 8 bits that can either be 1 or 0. As you have now learned, in decimal, the count would come to 9, and you would add another digit and reset. In binary, the same thing happens, but in this case, only 2 digits are used. To progress the count, you move the number left. Move the 1 to the left until all configurations of 1s and 0s have been used, at which point you add another 0 to the end. At this stage, all the numbers are reset to 0 apart from a single 1 at the beginning. Let's explore it step by step. Start to count with a 0, then add 1. To get to 3, start back at 0 again, but add a 1 on the left. As soon as all the 1s are full, start back at 0 again and add 1 to the number on the left. But that number is already at 1, so it also goes back to 0, and 1 is added to the next position on the left. Binary has many uses in computing. It is a very convenient way of translating electricity into computer code. If a signal is present, a 1 is displayed. Otherwise, a 0 is used. The binary counting system allows these base 2 signals to amount to a significant amount of information, transportation, and storage. This is the same way as Boolean numbers are stored. A Boolean value is either 1 for true and 0 for false. Some powerful applications can be built using this simple information representation. The ASCII, American Standard Code for Information Interchange, is a map of binary to character encoding, or a mapping from binary to text. There is a binary number reserved for each digit and character, as well as for a number of special characters, like a question mark, brackets, full stop, and even the spacebar. It was already mentioned that a byte is made up of 8 bits. Each bit can take the value of 0 or 1. So that raises the question, how many different values can be represented in each byte? Here we would use exponentiation, or counting the power of a number. An example would be 2 to the power of 3. That is 2 multiplied by 2 multiplied by 2, which equals 8. Now consider that you have a lock with 4 different digits. Each digit can be a 0 or a 1. How many potential pass numbers can you have for the lock? The answer is 2 to the power of 4, or 2 times 2 times 2 times 2 equals 16. You are working with a binary lock. Therefore, each digit can only be either 0 or 1. So you can take 4 digits and multiply them by 2 every time, and the total is 16. Each time you add a potential digit, you increase the possible permutations. So, the same lock with 5 digits would have 2 to the power of 5, or 32 different combinations. Now, coming back to our original question, how many different representations can there be in a byte? It was already mentioned that a byte is made up of 8 bits, which can be either a 0 or a 1. 8 bits would have 2 to the power of 8, or 256 different combinations. In this video, you learned about binary numbers, the language of computers. While at first glance it seemed quite limited to on or off, you learned that through the use of positional encoding, it could be used to represent a much larger number set. You learned how computers can use electricity to store and read numbers, and how exponentiation, or counting the power of a number, relates to counting unique states, and how to use it to count the number of possible combinations a number lock could have. Binary is the language of computers. Understanding how it is used to store information will give you a greater understanding when discussing data and the structures that hold it. In a previous video, bytes were introduced. Each byte consists of 8 bits. A bit is the simplest form of computing memory. In this video, you will learn about the Central Processing Unit, or the CPU, and the roles and functions of the different types of memory. Typically, a computer will be made up of a series of memory blocks, which contain both information and instructions on how this information needs to be processed. Memory capacity then refers to the number of bytes that a computer can hold. There are different types of memory that need to be considered, namely cache memory, main memory, and secondary memory. Firstly, to better understand the various layers of memory, it is important to pause and consider how a computer works. A computer functions around the Central Processing Unit, or CPU. This takes both information and some instructions on how this information is to be processed. All this information exists as bytes, or a series of ones and zeros that are determined by a small electrical current. The CPU can work faster than information can be transferred to it. Often, a CPU will be working on a number of different tasks near simultaneously. The switching between tasks can allow information to be transferred into the cache for processing and the results to be stored in the appropriate location. The proximity of a memory cell to the CPU can reduce the time it takes to load the information. Therefore, quicker and more expensive memory is always found near the CPU. So, an important concept to consider when discussing memory is the transfer rate. This relates to the speed at which a computer can transfer memory into the cache for processing. Now that you better understand the processing part, let's explore the different types of memory and start with cache memory. Cache memory is the most expensive form of memory and lives close to your CPU chip. When the CPU receives an instruction to process some information, it first checks the cache to see if the information is here. If the information is available in the cache, it is processed. If it fails to find the required information here, the information is not processed. The CPU then queries the larger, slower main memory, then loads this information into the cache for processing. Storing recently accessed information in the cache can improve the effectiveness of your system by reducing the search and transfer time of regularly used data. Much like a metro in a large metropolis, cache memory is organized in zones of importance. The most readily required information is in Zone 1. Each subsequent zone is of lesser importance and is numbered Zone 2, 3, 4, and so on. Next, you will learn about main memory. A computer's main memory consists of read-access memory, RAM, and read-only memory, ROM. Main memory holds only the information that a computer is currently working on. It can be volatile or non-volatile. Volatile memory stores information actively, so if the computer loses power, it is lost. Non-volatile memory retains its information when the power is cut. ROM, as the name suggests, is read-only, meaning the information cannot be overwritten. This memory is programmed once at the factory and cannot be altered. Typically, one will find instructions and data that are critical for a computer's function here. ROM is busiest when the computer starts and information on the required application is loaded. RAM is programmable. It can retain new information and instructions. RAM holds the current data and instructions that are in current use. The amount of RAM your computer has is directly correlated to how fast it can go. This is because of the transfer rate. Large amounts of RAM mean that the system does not need to transfer information constantly. Instead, it can hold and run a number of applications at once using RAM. All the memory needed to operate these applications needs to be available from your RAM. Having too many programs open will affect the performance of your system by exhausting your RAM memory. There are a number of algorithms for reading and storing these memory addresses that fall outside the perimeters of this course. Now, let's explore secondary memory in more depth. Secondary memory relates to external memory that can be plugged in externally and used to increase the storage capacity of your system. Accessing secondary memory is slower and requires transferring all required information and instructions into RAM. Examples of secondary memory would include cloud storage, external hard drives, and memory sticks. In this video, the various components of memory have been discussed. You have learned how all memory allocation revolves around the CPU, which oversees the reading, processing, and storing of information on the computer. You have also learned how there are different types of memory that vary in speed and importance. This informs their proximity to the CPU, with quicker, more expensive memory cells found nearer the source. This information should assist you in understanding how your computer works much better. When developing applications or evaluating efficiency, it is always useful to have a metric or a lens through which you can evaluate fitness for function. Evaluation in computer science will often consider two aspects, namely time and space. In this video, you will learn how to evaluate time efficiency or gauge performance by the time taken to complete a task. You can refer to this as the time complexity of a task. An application must return information within an acceptable time frame. These days, people expect an instantaneous response when clicking on a website. There might, however, be some extra scope afforded to more complex queries depending on the user's needs and expectations. Big O notation is a metric for determining an algorithm's efficiency. Put simply, it gives an estimate of how long it takes your code to run on different sets of inputs. In this video, the amount of time an algorithm will take is considered. Some of the big O notation you will encounter include the following: O of 1, O of log n, O of log n, O of n, and so on. So how do you measure the quickest possible time that something can be computed? You make use of a constant time algorithm where it takes O of 1 time to compute. Put simply, it means that no matter what is entered into a system, it will only take one computation. A simple example to illustrate this is to consider printing the first item in an array. In this instance, no matter how many values exist in the array, the approach has a big O of 1. Things can get more complex if you need to do a search. Consider that you have an array of 10 items, and you wish to know if a certain value is in this array. You might apply a loop and check each item to see if the value exists. In this example, the complexity is said to be O of n. This is called linear time. The search is going to be equal to the length of the array passed. The larger the array, the more time is required to search it. So, if in place of 10 items you have 100 items, then the search will take 10 times as long. Let's explore an example. Each operation comes at a time price for time complexity. So, O of 1 means it costs one single computation, and O of n means it costs n computations. For example, you wouldn't say it takes 45 seconds, you would say the complexity is n. So for every n action, that is plus 1 on our final result of complexity. If n equals 100, it is 100 checks. The complexity is still O to n, only n means it is 10 times longer. This means that your application speed depends on the size of the data being processed. Print array at position n is an example of an O to 1 operation. That means print the doc at whatever n is. It doesn't matter how big n is, the cost is always 1. Let's continue to O of log n. This search is less intensive than O to n, but worse than O to 1. O of log n is a logarithmic search, so it will increase as new inputs are added, but these inputs only offer marginal increases. A good example of this in action is a binary search. Imagine you are playing a guessing game with the following prompts: too high, too low, correct, given a range of 100 to 1. You may decide to approach the problem systematically. First you guess 50 and it is too high. Then you guess 25 and it is still too high. You then decide to go 12 or 13. It is still too high. What is happening here is that you are halving the search space with each guess. So while the input to this function was 100, using a binary search approach, you should come upon the answer in under 6 or 7 guesses. This solution would be said to have a time complexity of O log n, even if n, the range of numbers entered, is made 10 times bigger. It will not take 10 times as many guesses. Let's move on to O(n squared). O(n squared is heavy on computation. This is a quadratic complexity, meaning that the work is doubled for every element in the array. A good way to visualize this is to consider that you have an array of arrays. The first loop will equal the number of elements inputted, namely n. The second loop would also look at the number of input elements n. So, the overall complexity of running this approach can be said to be n times n, which is n squared. So, how will you visually represent the problem? This graph displays the algorithm for time complexity. The x-axis relates to the number of inputs and the y-axis relates to the time taken. Notice that as the number of inputs increases, it has a different impact on the gradient of the line for all cases but O of 1. In this graphical representation of how n relates to the number of computations taken, the best time to aim for is O to 1. O of log n is still very good. O to n is acceptable, and O(n squared) is not great. Of course, it is not always possible to tell how long an approach is going to take. Let's return to the example of looking for something in a loop. While you could say that to search a loop takes O to n time, this might not always be the case. Consider that the item being searched for is the first in array. Then the return will be in O1 time. Pretty good. Equally, the element might be missing, so every item must be searched. O(n time. The middle case would be that it is found around the middle of the loop O of n over 2. When evaluating an approach, there are 3 definitions used: best case, worst case, and average case. To conclude, in this video, the notion of time in relation to complexity was introduced. You have been given something to consider when implementing a solution to a problem. A good question to ask yourself before you start is how many computations does my solution employ, and is there a better way? Now that you use a metric to evaluate your solution to a given problem, you can start thinking of its efficiency in relation to time complexity. This is not the only way to consider a solution, and in the next video, the focus will be placed on space complexity. In a previous video, you learned that the time spent on an algorithm depends on the problem's complexity and data structure. Another consideration when evaluating suitability is space. How much memory will a given solution take? This is often a trade-off with time. The selection of this data structure will pivot on what your priority is: speed or compactness. Some algorithms, like the hash tables you learn about later in this course, provide very fast lookups in O of 1 time. However, to work efficiently, they must have a lookup for every element stored. This results in a space complexity of O of n. The big O notation for space complexity is the same as for time: O of 1, O of log n, O of log n, and so on. In all these notations, n refers to the size of the input. This is often measured in bytes. Different languages have different memory costs associated with them. In Java, for instance, an integer requires 4 bytes of memory. A blank array will consume 12 bytes for the header object and an additional 4 bytes for padding. Thus, if n refers to an array of integers size 4, then the total memory requirement is 32 bytes of memory. When discussing space complexity, you have to consider what the increase in input size has on the overall usage. The space complexity of a problem can be broken into two sections, namely auxiliary and input space. Auxiliary space is the space required to hold all data required for the solution. It refers to the temporary space needed to compute a given solution. Input space refers to the space required to add data to the function, algorithm, application, or system that you are evaluating. Consider when you are learning long division. You may have been taught using a methodical approach that involved breaking each computation into simpler steps. To achieve this, you would create a table to hold the temporary calculations. Some complex problems require the same additional allocation of space to hold their workings temporarily while the solution is being calculated. Big O space complexity allows for the auxiliary space required for coming upon a given solution. So it can be said that space complexity equals input space plus auxiliary space, that is, the space required to compute a result. Remember that you calculated the space complexity where an integer requires 4 bytes of memory. You added the 12 bytes of the header object and the 4 bytes for the padding. The total was 32 bytes. However, consider that the size of the array is doubled to 8 integers. Space complexity is now computed the same way, and the total will be 48. The space complexity is higher. Adding additional input did not increase the size of the auxiliary space, so when computing the big O, you can discount the auxiliary size if it is not impacted by increasing the input size. Knowing that each decision made in computing a solution requires memory, it is worth noting the aspects that can increase memory usage. Some common memory actions could be assigning variables. These can be temporary variables when computing a solution, as with the long division analogy before. Creating a new data structure. Some solutions require that a new array be created to contain the values or a duplicate array that retains index locations. Creating a new data structure instance has an O to N auxiliary memory cost. Function calling and allocation also have additional memory overheads. It is worth bearing in mind how space is being used when designing an application. Creating a new variable to contain a value in place of overwriting an existing one will impact your space efficiency. This impact is greatly increased if you needlessly copy arrays or complex data structures with high data overhead. Additionally, writing functions that use complex structures when simpler, less intensive structures will suffice can incur a penalty, particularly if these structures need to be duplicated in computing a solution. In conclusion, in this video, the concept of Big O was expanded from one focused on time consideration to one that includes space complexity. It was highlighted how there is often a trade-off between speed and memory efficiency. Additionally, there were some observations on the efficient use of space when designing a solution that is worth bearing in mind. Well done! You've reached the end of the introduction to the coding interview module. Let's take a few moments to review what you learned during this module. You began the module with a course introduction, where you were informed of the content of the coding interview prep course. You then moved on to the coding interview lesson. Your first lesson focused on the technical coding interview, primarily to determine that you are technically capable of the role's responsibilities. You learned about the steps that you must keep in mind when this interview is conducted. You were taught that using the appropriate tools is always important, and that you have to keep time constraints in mind. You then learned about code optimization and should be able to write or rewrite code so a program uses the least possible memory or disk space and minimizes CPU time or network bandwidth. To summarize, you learned about some approaches that can be used regardless of the challenge presented. Even if you are not familiar with the problem or don't achieve a result in the time allotted, always strive to demonstrate your reasoning and best practice approaches. Prepare for technical interviews by practicing solutions to online problems and, when possible, employ a similar methodology to each challenge. This will assist you in the future, so that regardless of the challenge faced, you are working from a comfortable framework. You then focused on communication and the importance of first impressions. You were introduced to verbal and non-verbal communication and the importance of both. You learned about the STAR method and how to use it to your benefit when communicating with interviewers. You should now be able to look at the context of a situation and the challenges faced, the responsibilities around the tasks involved, the actions required to address the challenges, and lastly, the outcomes that need to be achieved. To summarize, you should now be able to clearly convey a concept during an interview. Communicate why you are suitable for the role in a verbal and non-verbal manner. Finally, use the STAR method for engaging with technical questions that will arise over the course of an interview. You then moved on to the next lesson, where you were introduced to computer science. You started with binary, where you learned about the difference between base 10 and base 2. You then discovered positional notation. This is the use of the position of the number to denote a progressive increase in value. You were then introduced to how a computer stores data as bytes, and that each byte is made up of 8 bits that can either be 1 or 0. You were also given some examples. You examined the concept of exponentiation, or counting the power of a number. This was followed with examples where a lock with a different number of digits was used to explain the concept. You should now be able to apply this knowledge and understand that binary is the language of computers. Next, you explored memory. The first concept you learned about was memory capacity, which refers to the number of bytes that a computer can hold. You also learned about the different types of memory that need to be considered, namely cache memory, main memory, and secondary memory. You should know by now that to better understand the various layers of memory, it is important to pause and consider how a computer works. You learned about the transfer rate, or the speed at which a computer can transfer memory into the cache for processing. You then explored cache and secondary memory and should be able to describe the differences. You were then introduced to the concept that a computer's main memory consists of read-access memory, RAM, and read-only memory, ROM. You should be able to describe the role of the main memory and distinguish between RAM and ROM. You should now be better positioned to work with memory. You then moved on to explore time complexity, where you learned how to evaluate time efficiency or gauge performance by the time taken to complete a task. You discovered Big O notation, which is a metric for determining an algorithm's efficiency. Thus, it gives an estimate of how long it takes your code to run on different sets of inputs, or it considers the amounts of time an algorithm will take. You were given some examples and should have a solid idea of how to measure time complexity. You then learned about space complexity. It is not just the speed of an algorithm that is important, but also how much memory will a given solution take. To understand space complexity, you were introduced to the concept of auxiliary space, which is the space required to hold all data required for the solution, also referred to the temporary space needed to compute a given solution. The other concept was input space, which referred to the space required to add data to the function, algorithm, application, or system that you are evaluating. To summarize, space complexity equals input space plus auxiliary space. That is the space required to compute a result. You have done some quizzes on all the topics mentioned. That's a great start to your learning journey in this course, and all this content should empower you to have excellent coding interviews in the future. Having a knowledge of data structures is useful for any coding interview you may encounter, from basic data structures like strings, booleans, or arrays, to more advanced data structures like collections, graphs, and heaps. Understanding the data you are working with and the most appropriate structure to use can be very beneficial. In this video, you will be introduced to data structures and the two main types, mutable and immutable. You will also learn what to look for when considering a given data structure in your own applications. A data structure models an object so that it can be stored and organized easily in computer memory. It can be a simple, immutable structure that does not change after creation, or it can be a mutable structure that facilitates operations to be performed on the contents. Operations might include updates and queries to be performed on the contents of the structure. On the surface, it may seem that a mutable structure should always be used. However, mutable structures require time and effort to model, and some objects are very complex and not easily modelled. Other concerns, such as space, may be a factor. Understanding the underlying mechanics of data structures can be a great advantage because decisions to use a particular data structure can have far-reaching implications on a project's progress. While the implementation and capabilities of a data structure can range between various programming languages, the overarching architecture generally follows similar patterns. Here is a universal classification of data structures that categorizes the different types of structure into two main branches, linear and nonlinear. This relates to how the elements are stored within the data structure. A linear structure relates to how the information is stored. The elements of the structure are arranged one after another or sequentially, reflecting the order that they were inputted. Examples of linear structures are arrays, queues, stacks, and lists, and it infers that each element is attached to the element that precedes it. Some languages will demand that only similar types of data are stored on the same structure. Therefore, you will have integer lists or string arrays. Other languages will allow for mixed arrays. This would mean that storing an integer and string in the same array is not prohibited. This easy approach can come at the cost of error handling down the line. For example, imagine you have created an array and want to find the sum of your values, only to discover that the total is 3 pineapples and 1 apple. Once a simple structure has been created, such as a list or array, it will contain an index. An index is a way of accessing elements that may not necessarily be the first or last instances. Generally, use of an index is done through appending square brackets and the location of the item as an integer. So array 4 would indicate that the required element is the 4th item of the array. However, programming languages are predominantly zero-based, which means that the count will start at 0. Therefore, array 4 would actually be the 5th item in the array. Accessing an array through the use of an index can throw an error if index location 8 is requested, but there are only 7 elements in the array. A common feature of these structures is that most languages have a built-in length method that will inform as to how big an array is. An example of this would be calling array.length in Java or placing it inside a len function in Python. While the mechanism of how to retrieve the length varies, it is possible in most programming languages. Arrays and lists are typically first-class objects. This means that all functionality that is available to other variables is available to them. This definition generally indicates that a data structure can be passed as a parameter to a function, returned as a result, or assigned to a variable. When passing a list or array to a function, care should be taken that the structure is actually passed and not just a reference to the structure. This can be a memory-saving device used to prevent copying the information. However, such instances can cause an error if a change in the structure inadvertently affects the array in the calling environment. In this example, a string has been added to a list of integers, and because the new list points to the initial list is also changed. Therefore, it is better to make a copy of the array and pass the copy to the function. Another memory-related issue to be mindful of is memory leak. Memory, as previously mentioned, can be arbitrarily allocated. If this memory is not used, then it is good practice to deallocate the memory location. As a result of careless programming or other issues, it is possible that a program makes repeated calls that result in excessive memory being allocated and not then deallocated. Over a prolonged time, or through repeated calls, this can cause the application to run out of memory and crash. Most compilers have sophisticated algorithms for detecting and deallocating memory to avoid this issue. In contrast to linear structures, there are nonlinear instances such as trees or graphs. These structures do not allow you to traverse the data in one smooth motion. Instead, you can investigate certain paths. The makeup of these structures means that they can include natural sorting, which makes querying for specific data very quick. You will learn about different types of sorting later in the course. In this video, you had a general overview of data structures, including their two main types, linear and nonlinear. You have also learned about some of the considerations that should be made when deciding the type of data structure you should use. As you progress through this module, you will explore these structures further and learn about some of the individual strengths and weaknesses. Have you ever needed to store some data but were unsure about what sort of data structure to use? It's a common coding problem. In this video, you will discover two important data structures that could be used, lists and sets. Both are very useful data structures with their own strengths and weaknesses. Lists and sets are common in many programming languages. Let's get started by exploring lists. In most programming languages, lists are represented as objects. This means that in addition to storing data, they also have their own inbuilt methods. Here, an inbuilt sort method is used to arrange the numbers in a list. As with arrays, it is common to find lists that are declared as either a string, an integer, or float. In some programming languages, you can have lists with mixed element types. A list is an abstract concept that refers to a container of elements. A stable implementation of a list is done using either an array or a linked list. An array-based list is an ordered collection built using arrays as the underlying data structure. As such, they are subject to the same strengths and limitations associated with arrays. Array-based implementations relate to the initial sizing, rather than simply pointing to another node, as with a linked list. Some languages require that you initially determine how big a structure will be, while others allow for dynamically growing structures. It should be noted that this freedom is somewhat surface level. For many dynamic structures, there is an initial size automatically configured at instantiation. When this limit is reached, the array will copy itself into a new structure with a larger size allocation. Therefore, the decision not to arbitrarily allocate space at the onset may come at a cost at runtime, when such data structures may have to expand multiple times during the execution of other operations. Consider the computation costs of a list dynamically growing while performing operations in a loop. In this case, it would help to set the initial list size to be larger rather than dynamically growing, which can be costly due to having to create and copy over values into increasingly bigger lists. A linked list works differently. A linked list contains two pieces of information, the data and a pointer to the next list item. A linked list begins with an empty list and can grow dynamically by introducing new cells to the list. To grow a linked list, you simply have to add a new node and point the list at its location. This makes them very fast for storing large amounts of data. The flexibility of linked lists is achieved by including some additional storage requirements. Notably, in each node, there must be some reference to the nodes around it. There is also a head and a tail. The head is a unique node that indicates that it is the start of the list, and the tail indicates where the list ends. This approach to growing the size of the data structure is very powerful and can lead to very large but manageable datasets. So, what do sets entail? Set is very similar to a list. However, a set will store its elements in an unordered way. Though there are some possible implementations of ordered sets, sets have some unusual tendencies. A set will only hold unique elements. So, adding an element that already exists to a set will make no difference to the data stored there. The unordered process in which sets store their information means that printing out a set will not necessarily reflect the order in which the element was added to the set. Once a value has been added to a set, it cannot change. Instead, you would have to delete it and add a new value instead. Sets are exceptionally fast to search. This is because of its internal mechanisms. A set uses hash tables to determine where to store the elements of a set. Therefore, each number that is passed to a set will have a hashing function applied to it. A hashing function can be defined as an algorithm that takes in some data and maps it to a fixed size value. The value is theoretically unique, and every time the function is applied to the data, the same value is returned. This means that searching a set can be done in O1 time. This is due to the mechanism that is used to save values in a set. You will learn about hashing functions in more detail later in the course. A ON approach would be to iterate over the entire data structure to check for the presence or absence of a value. Sets instead apply the mapping function to the input data and check the resulting output to see if a value exists there. If it does, then the value is returned. If it doesn't exist in the set, then the data was not stored in the set and hence will return a false. While sets can perform an exceptionally quick search, performance degrades when dealing with very large data sets. This is due to the nature of the hashing function. The more values retained, the more risk there is of clashing. Clashing is when the hashing functions return the same unique mapping for two different values. The larger the dataset used, the more likely clashing is prone to happen. So, there we are. In this video, you have explored two very important and useful data structures, lists and sets, and learned about the strengths and weaknesses inherent in both. You should now have a greater sense of when to use each, depending on the storage needs of the solution. So, what is the difference between a stack and a queue? And what does it mean to use one of these data structures over another? Well, in this video, you will learn about stacks and queues, the difference between the two, and why you might choose to use one over another depending on the requirements of the solution. Stacks and queues are abstract data structures that have many different implementations depending on the programming language. The unique principles that are common to both are how elements are added and removed. While lists and arrays allow for random access, stacks and queues employ sequential access. This limited approach to holding data can be very useful when you want to control how the data is accessed. Let's start by exploring stacks in a little more detail. Stacks are linear data structures with strict ways of adding and removing items. As the name suggests, a stack is a collection of elements that are stacked on top of one another. What this means is that it is impossible to pull items from the middle. Instead, a stack works with a strict first in, last out or FILO basis. This can also be phrased as last in, first out or LIFO. It's a simple yet powerful concept that informs you that items can only be retrieved from the top of the stack, which determines the order in which you can retrieve them. An example of this principle in action is hitting Ctrl-Z in a URL, Word document, or any coding environment. Ctrl-Z undoes the very last action. Hitting it again will undo the previous action, and so forth. To extend the analogy, Ctrl-Y will redo the action or push it by adding it back to the stack. Stacks tend to have very few methods: push, pop, is empty, is full, and peek. The functions of these methods correlate with their names. Push will add an item to the stack, and pop will remove it. Is empty checks that the stack contains nothing, and is full is a Boolean that will return true if there is no more room in the stack. You might have heard of the popular computer question and answer platform named after this very issue, namely Stack Overflow. So, popping an item takes it from the top of the stack, and calling pop again will return the next item in the stack. Pop can be called until there is nothing left in the stack. Push then will place an item on the top of the stack. It is worth noting that by calling pop or push, you are changing the stack. You have now learned about all the methods except peek. So what does that entail? To have a look at the contents, one would call peek, which allows you to view the top item without removing it from the stack. So calling it will not change the state of the structure, unlike pop or push, which permanently alters the stack. Some implementations will include a search feature for looking through the stack, though this won't always be the case. Now, let's explore an example. Imagine that an application generated a deck of cards. You could create a stack of 52 playing cards, and each time a card is dealt, it is removed from the top of the stack, just as in a real deck. Using a stack in this way would simplify the code required for maintaining the state of the deck. Now, let's explore queues. A queue is very similar to a stack in that it tends to have the same methods. It can create, insert, remove, and check the state of the queue. Unlike a stack, a queue works on a first in, first out, or FIFO basis. Again, the name is a good indicator of how the structure works. As an example, imagine you have a line of people waiting to get a burger at a fast food restaurant. The first person to enter the queue gets served, and each subsequent customer stands behind the one in front and is processed in turn. As with the stack, a queue will pop the selected item from the structure, though different languages have different implementations for this. The element that is removed from the queue is the one at the bottom. In other words, the least recently added item, or the first to join the queue. Using a real-world IT example, a server balancing system usually uses a queue to retrieve tasks. The structure would hold each task in order of insertion, and when a server becomes available to process the task, the first task entered into the queue would be removed and passed to that server. In this video, you have learned about stacks and queues and the differences between them. These are very useful tools to have in your programming toolkit, and knowing them will be an advantage when dealing with problems requiring a structured way of accessing and inserting data. In previous videos, you have learned about data structures like lists, stacks, and queues. Another data structure you have not yet learned about is trees. So what exactly is a tree in the data structure context? Trees are a powerful data structure that gives you great flexibility in adding and searching values. The inherent structure of the tree can allow you to understand a lot about the relations between the data stored, which can save a lot of time and code when extracting information from the data. In this video, you will explore the general structure and inherent features that trees provide. You will also learn about some of the different types of trees and the advantages of using a tree data structure. So, let's get started. A tree is a very complex data structure that resembles a tree in design. It consists of nodes that are linked with one another. A node can be a parent or child node. A parent node may have a connected set of children nodes. Nodes with no children are referred to as leaf nodes. As with a tree, nodes can branch off in different directions, allowing for powerful search and storage features. Generally, we can look at a tree as a graph-like structure that has nodes that contain data and edges that model how each node relates to one another. When discussing trees, it is important to know some of the terminologies. The top-level node is referred to as the root. Each subsequent node down that is connected to this node is referred to as a child node. Nodes that have the same parent are referred to as siblings and are considered to be on the same level. One might picture a chapter of a book where the subsections correlate to connected nodes. The theme of these nodes will be of a very similar nature. Other branches would be other chapters that still fall under the general theme but on different topics. A path refers to a series of connected nodes. You might assume a connection between two nodes by determining the shortest path. This is to say, the quickest way that you can move from one node to another. Intuitively, nodes with shorter paths will have more in common. The depth of a node refers to how many edges there are from the parent to the root or the longest path. The height of the tree refers to the number of edges between the topmost node to the deepest node within the structure. And finally, the size of a tree refers to the total number of nodes within the tree. There are many variants and implementations of trees, such as binary trees, B trees, and B+ trees. There are also quad trees and AVL trees, to name a few. While all of them will contain the general theme outlined, their use and implementation differ slightly, depending on the type of tree being applied. There are many advantages to storing your data in a tree-like structure. The connections between the nodes indicate a relationship that is inherent in your data. They can store information in a hierarchical fashion, where the topmost content is stored in the upper nodes, and more in-depth information can be retrieved by traversing a given branch to a tree. They are also very efficient for inserting and deleting data due to the flexible way in which they are implemented. The non-linear nature of a tree means that there are many ways of traversing the data. In binary trees, this feature can be very useful when storing data. A left node has a lesser value, while the right node indicates that there is a greater value. Let's demonstrate that with some data values. The first data contains the value of 23. Then a 4 is added. Because it is less than 23, it goes to the left. Following is a 1, also less than 23, but also less than 4. That also goes to the left. The next number to follow is 30. Because it is now larger than 23, it goes to the right. A 24 is added, and because it is less than the 30, it goes to the left. But the 56 that was added goes to the right of the 30 again. One can traverse a tree in depth first or breadth first method. A depth first method involves visiting every node from top to bottom sequentially. A breadth first method involves searching each node on the same level before ascending to the next level and repeating until the root node has been reached. More benefits of trees are that they can be used to model file systems on your laptop, class hierarchies like those found in Java, or modeling hierarchies in organizations. In this video, you explored the general structure and inherent features that trees provide. You also learned about some of the different types of trees and the advantages of implementing a tree data structure. At this point of the course, you have been introduced to several different data structures, and you've discovered that there's not a perfect way of storing information. Instead, there is a wide variety of approaches, each of which is an appropriate solution depending on the problem. In this video, you'll learn about what a hash table is, its structure and inherent features, and how it works. You will also explore some of the advantages of using hash tables and discover what is meant by collisions in hashing. A hash table contains several slots or buckets to hold key value pairs. It requires a hashing function to determine the correct bucket to place the data into. A hashing function is any algorithm or formula that is applied to a key to generate a unique number. Each data item to be stored must have a key and a value. The key is taken, and the hashing function is applied to it, such that it is reduced to a fixed size value. There are a variety of hashing functions one could apply. You may be familiar with them in relation to compression. When you want to send information over the internet, you might first compress the size of it to a manageable number of bytes, send it over the internet, and then decompress it on the other side. This is an example of how hashing works. It reduces the key to a small, manageable size, which then acts as the index indicator. What information is used to generate the index is dependent on the application. It might be the data itself, if it is small enough, or it might be the last 4 digits of an employee ID number, or it might be a key in a dictionary. Most programming languages have built-in hashing functions like MD5, SHA, or CRC32. So, implementing a hashing function is a straightforward job. When discussing big O notation, the idea that speed and space are often at odds with one another was introduced. This means that you can reduce the time taken to retrieve an item, but in doing so, you add overhead to your application. Hash tables prioritize speed over space and can retrieve an item in O of 1 time. Recall the discussion on arrays. When you want to check if a value exists, a search must be executed that checks each element of the list and makes a comparison with the target value. Worst case scenario, this will take O of n time, or in other words, if the element was at the end of the array, it must make n checks. Hash tables offer an alternative approach to storing and searching data. This is done through use of an index. To achieve this, you must implement an algorithm that takes in a key and maps it to a value which is stored in an index. Then, when a new key is presented, the algorithm need only run the same function and determine where in the index the value lies. Much like an index in a book, this will drastically speed up the time it takes to identify the location of some data. You are likely to find hash tables used in caches, dictionaries, database indexes, and sets. Consider a scenario where you have an array of 10 keys which are numbers 0 to 9. You elect to employ a hashing function to decide where in memory to store these numbers. You opt for a simplistic approach of applying the modulus of 20 to the numbers. So, for each key from 0 to 9, you apply your hashing function. Start with 0 mod 20 equals 0, 1 mod 20 equals 1, 2 mod 20 equals 2, 3 mod 20 equals 3, and so forth. In this way, you would generate 9 unique values which are used to represent in memory where the data associated with those keys is placed. This example is simplistic but illustrates the mechanism behind creating hash maps. The issue arises when the number of keys to be stored grows beyond 20. Remember 1 mod 20 equals 1, but 20 mod 21 also equals 1. Let's move on to collisions in hash tables. What are collisions in hash tables? A hashing function will apply a clever algorithm that will reduce the size of the key to a manageable size. Some approaches are more intricate than others. So, what happens if the result of 2 hashings is the same? To expand on this idea, it is worth pondering on von Mises' birthday paradox. Due to probability, sometimes an event is more likely to occur than we believe it to. In this case, if you survey a random group of just 23 people, there is actually about a 50-50 chance that 2 of them will have the same birthday. This is known as the birthday paradox. Say there are 24 employees in a company and a clever hashing function has been applied that takes the date and month of their birthday and uses this as an index. With only 24 employees and a hash table of 365 index slots to hold a reference to them, you may think that the probability of any 2 employees sharing a birthday is unlikely. In fact, it has been shown that it is over 50% likely to occur. Next time you're at a party, be sure to check if any 2 attendees have the same birthday to check for yourself. What this illustrates is that there will be duplicate hashes generated when the hashing function is applied to the key and that allowances must be made for it. There are a few solutions to the issue. One solution is to grow the table every time a collision occurs, then increase the complexity of the hashing approach, redistributing the values to new addresses. In this way, a table will grow organically to match the size of the data required. Another is to create a linked list at the point of collision and simply store the additional values. So, in the event of a collision, instead of storing a value, you would instead store a linked list of values. In this video, you discovered what hash tables are, their structure and features, and how they work. You have also learned that hashing is a very clever approach to generate O of 1 time searches using a hashing function and an index. You explored collisions and how they can be used to inform the size of the table, And you even learned that if you are at a party with more than 24 guests, it is more likely than not that at least 2 will share the same birthday. A heap may not sound like a particularly promising name for a data structure. However, it is a very important organizational tool and combines some features and benefits of other data structures. In this video, you will learn about the structure and features of heaps. You will also discover how heaps can be used to organize elements from least to most important, and how, by limiting the functionality of heaps, productivity can be increased. So, let's get started with heaps. A heap is a specialized data structure that is modeled like a tree, but behaves in a similar way to a queue, though with a notable difference of assigning priority to some elements. Each element in a heap has a key value, and the priority can either be the smallest or the largest key value. Heaps that place priority on the lowest valued key are called min heaps, and ones that place the priority on the maximum value are called max heaps. Heaps were first introduced as a means of storing and searching data efficiently, but since then it has been recognized that there are a number of very useful operations that a heap can be applied to. A heap has a few select core operations that it can perform: insert, find_min, and delete_min for a min heap, and insert, find_max, and delete_max for a max heap. For the rest of this video, the discussion will revolve around min heaps, but you can reverse everything said and it will apply to a max heap. The only difference between the two is where the priority is placed. As with many of the data structures discussed on this course, these methods are the fundamental elements that constitutes a heap. Different implementations in different languages could have additional methods added. An instance of which may be decrease key. This is where the value of a key is changed, the motivation for which would lie with the priority of the key in real-world instance changes. When discussing trees, it was mentioned that binary trees sort values in order of size. If the value is less than the node, go down the left path. If the value is greater than the node, go down the right path. Because of this underlying architecture, heaps are often built using binary trees, though another approach would be to make an array act in a way that mimics the behavior of a binary tree. The minimum value is placed on the root node, and each subsequent value is placed on the hierarchy where their value dictates. This means that to retrieve the minimum value from a heap is O of 1, because it will be stored always at the root. Unlike a stack, retrieving a value does not cause it to be moved from the tree. Instead, a delete min method exists that can be called if the intent is to remove items as they are processed. Typically, a heap would not support operations such as deleting items other than the priority element. The reason being that a heap is built for specialized purpose that involves identifying the most important item and returning this in the shortest time possible, then queuing up the next item of importance. Deleting items in the tree would require restructuring the tree, and this would lead to a degradation in performance. If you are looking for a data structure that can act in this way, then you might consider structures other than a heap. Insertion into a min heap is done through propagation. Each item is inserted at the root. A comparison is then made with the left value. If this is less than the newly inserted item, they are swapped. This continues until the newly inserted item has no greater value above it, and the value below is lower. Insertion in a heap can be achieved in O of log n time. Having examined the underlying mechanisms that power a heap, you may now have some idea of how this data structure can be applied. Considering that its inherent structure prioritizes a particular value from a group of elements, the natural application would be for scheduling. This could apply to CPUs, routers, or packet handling. Additionally, one could imagine that such a structure would be useful in prioritizing certain tasks like interview scheduling, where the key used to store the candidate may relate to what stage of the interview process they lie at, or what priority the role has within the organisation. Having a process that automatically applies schedules based on importance can be a huge time-saving device. In this video, you have gained a greater understanding of Heaps and how they can be used to organise elements from least to most important. You have been shown that by limiting functionality, productivity can be increased. As with the selection of any data structure, it is important to find the right tool for the right job. When considering a given problem in computer science, it is always important to consider what executions might be required to solve your problem, and through this reflection, choose an appropriate data structure to hold your data. Consider that you might work for a large internet company that wants to store a directory of locations and their connectedness to one another. In this illustration are cities plotted in relation to one another. Notice how every possible detail need not be recorded. Say, for instance, you want to know how far Chicago is from Boston. You can easily deduce this from the way in which the data is organized. The same approach could be used to model internet destinations, relationships between words, or people on a social network. This approach to saving information is a graph-based approach. In the coming video, some terminology and advantages to this approach will be outlined. This structure illustration is a graph that is made up of nodes to denote destinations, and edges that show how each node relates to another. The presence of values between the nodes means that this is a weighted graph. There are no arrows present, which means that this is an undirected graph. In contrast to a directed graph, an undirected graph has no order of precedence. One way to think about directed and undirected graphs is like two-way and one-way streets. Sometimes it helps when ordering data to highlight some progression, when in other instances, the edges are there just to show association. A path, then, is a sequence of two or more nodes that are connected by an edge. A connection in a directed graph is considered weakly connected if the edge is only one way. However, if there are two connections going either way between two nodes, then it is said to be strongly connected. At this point, you may be considering that a graph resembles a tree. In some ways, you can say a tree is a simple graph. Notably, a tree has a starting point and models a hierarchy with parents and children. A graph is a far more complex structure that has no beginning or end. Two nodes bordering one another are called neighbours, and nodes that are connected through a neighbour are said to be adjacent. Graphs like trees can be traversed breadth first and depth first. Recall a breadth first search involves visiting every node on the same level, then going lower, and a depth first search involves drilling into the end of every branch before moving on to the next one. A breadth-first approach involves choosing a given starting location and iterating over all the neighbouring nodes. Each neighbour will have a connection of connected nodes, which can be added to another data structure already mentioned, the queue. In this way, you can systematically visit every node. To achieve a depth-first search, you can employ a stack. Recall a stack processes elements differently than a queue. While the queue prioritizes first in, first out, a stack focuses on last in, last out. So, by placing all of the neighbor nodes systematically on a stack, you would ensure a depth-first traversal. Graphs are a much-studied data structure and are the basis of many algorithms that have been developed to establish importance between nodes. Regardless of the element stored in the node, one notable one is shortest path. What is the quickest way to get from node A to node E? The edge weights would inform as to the cost of choosing each path. This approach is used when routing internet packages on the internet, or when calculating a journey on Google Maps. Another common graph-based challenge is the traveling salesman. A salesman has a select few nodes to visit. What is the best route to plot that hits all the nodes in the shortest time? This would be used in package routing. Given X destinations and Y vehicles, plot out the most efficient route so that all packages get delivered with the least spending of resources. In this video, you learned how graphs give you the opportunity to model data in a flexible way that facilitates inferring information on the data by how it is stored. This versatile approach only retains the minimum of information. The distance from Chicago to Boston is not stored anywhere, but can be deduced. It's easy to query different questions without changing the makeup of the data. Calculating the best time when walking can easily be substituted in place of driving with minimal fuss. There has been a whole field of statistics devoted to inferring information from node placements, which can be levered to make inference on any data stored there. Well done! You've reached the end of the Introduction to Data Structures module. Let's take a few moments to review what you learned during this module. You started the module with a lesson on basic data structures. This ranged from basic data structures like strings, booleans, or arrays to more advanced data structures like collections, graphs, and heaps. Understanding the data you are working with and the most appropriate structure to use can be very beneficial. You learned about a simple, immutable structure that does not change after creation, and mutable structure that facilitates operations to be performed on the contents. You then took a deep dive into all the types of data structures. To refresh your memory, here is a universal classification of data structures that categorizes the different types of structure into two main branches, linear and nonlinear. Examples of linear structures are arrays, queues, stacks, and lists, and it infers that each element is attached to the element that precedes it. You learned about the structures in detail and should now be able to describe each of them. You then moved on to focus on nonlinear data structures. In contrast to linear structures, there are nonlinear instances such as trees or graphs. These structures do not allow you to traverse the data in one smooth motion. Instead, you can investigate certain paths. You then moved on to the next lesson, where you were introduced to lists and sets. You learned that, as with arrays, it is common to find lists that are declared as either a string, an integer, or float. In some programming languages, you can have lists with mixed element types. You also learned that some languages require that you initially determine how big a structure will be, while others allow for dynamically growing structures. That was followed by a section on linked lists and how they work. Remember that a linked list contains two pieces of information, namely the data and a pointer to the next list item. You then learned about sets and how they work. A set is very similar to a list. However, a set will store its elements in an unordered way. Following sets, you were introduced to the hash functions and their role in searching in sets. Sets are exceptionally fast to search. You then moved on to the next video on stacks and queues in the same lesson. To refresh your memory, stacks and queues are abstract data structures that have many different implementations depending on the programming language. The unique principles that are common to both are how elements are added and removed. You learned that stacks and queues employ sequential access and use the empty stack, push, and pop methods to move and/or add and remove items. You also learned about the FILO first in, last out, and FIFO first in, first out principles. When you visited queues, you learned that a queue is very similar to a stack in that it tends to have the same methods. It can create, insert, remove, and check the state of the queue. Unlike a stack, a queue works on a first in, first out, or FIFO basis. Again, the name is a good indicator of how the structure works. The last video in this lesson focused on trees. Trees are a powerful data structure that gives you great flexibility in adding and searching values. The inherent structure of a tree can allow you to understand a lot about the relations between the data stored, which can save a lot of time and code when extracting information from the data. You learned about tree structures and how data moves in a tree. In the next lesson, you were introduced to advanced data structures. First, you learned about what a hash table is, its structure and inherent features, and how it works. You also explored some of the advantages of using hash tables and discovered what is meant by collisions in hashing. Let's quickly revisit what this entailed. You were introduced to the hash function and learned that the key is taken and the hashing function is applied to it in such a nature that is reduced to a fixed size value. You learned about compression with an example from our field of experience. When you want to send information over the internet, you might first compress the size of it to a manageable number of bytes, send it over the internet, and then decompress it on the other side. This was followed by an explanation of how hash tables offer an alternative approach to storing and searching data through use of an index. To achieve this, you must implement an algorithm that takes in a key and maps it to a value which is stored in an index. The next video in this lesson focused on the structure and features of heaps. You also discovered how heaps can be used to organize elements from least to most important, and how, by limiting the functionality of heaps, productivity can be increased. You learned that heaps could place priority on the lowest valued key and are then called min heaps, and ones that place the priority on the maximum values are called max heaps. A heap has a few select core operations that it can perform, namely the insert, find, and delete of items. Following this, you learned that deleting items in the tree would require restructuring the tree, and this would lead to a degradation in performance. To summarize, in the video about heaps, you have gained a greater understanding of heaps and how they can be used to organize elements from least to most important. You have been shown that by limiting functionality, productivity can be increased. As with selecting any data structure, it is important to find the right tool for the right job. Finally, you focused on graphs and set the scene as follows. When considering a given problem in computer science, it is always important to consider what executions might be required to solve your problem, and, through this reflection, choose an appropriate data structure to hold your data. Consider that you might work for a large internet company that wants to store a directory of locations and their connectedness to one another. An illustration of cities plotted in relation to one another was used to explain all the concepts, such as a weighted graph, an undirected graph, and that in contrast to a directed graph, an undirected graph has no order of precedence. Following that, you learned that a connection in a directed graph is considered weakly connected if the edge is only one way. However, if there are two connections going either way between two nodes, it is said to be strongly connected. In this video, you learned about the key concepts and topics covered throughout this module. You have done some quizzes on all the topics mentioned. You are getting more equipped for your future. Good luck with the next module. Sorting a set of data might sound like a straightforward task, given what you have already learned throughout this course. However, it can be surprisingly challenging when you get into the details. In this lesson, you'll explore sorting algorithms and the different sorting methods that are available to you. You'll be introduced to some of the various approaches to searching, such as linear and binary. You'll also discover the steps involved in implementing both of these approaches and explore the advantages they offer. You'll also learn about the steps required for implementing selection, insertion, and quicksort, and discover the strengths and weaknesses of each sorting approach. There are several algorithms that have been developed for this challenge, and some data structures that had previously been discussed, like binary trees and heaps. Both of these data structures have been designed with the aim of retaining the data in a sorted manner. Working with sorted data or having the ability to sort your own data can result in significant time savings. Therefore, a data set of elements that can be ordered is fundamentally necessary. This order could be alphabetically, sequentially, chronologically, by size of shape, or by hue of colour. The actual metric that is used is less important than the fact that they can be arranged in an ascending or descending order. A second consideration that's factored in is whether the ordering is permuted, meaning reordered, or has been accomplished by creating a copy whilst keeping the original list. Selection sort is an early approach to sorting. It mimics how a human might approach the problem. The underlying principle is very straightforward. You start by searching through a list to identify the smallest element. Then, switch this with the first element so that the smallest element is placed at the top. Now the previous occupant of the top spot has been switched into the vacated spot in the list. This is repeated for every element in the list until the list has been ordered from the smallest through to the largest. Let's explore this in an example. You'll see in this diagram element 35 at index location 0. In a selection sort, a comparison is made between the element at index 0 and each element in the array until the lowest is found. Equally, element 46 in the next location is compared to each element and in this case switched with 6. Next is element 36 found at index 2. You'll notice that element 9 at index 3 is deemed the smallest. However, the entire array must be searched. This process is continued until every element is ordered by size, smallest to the left, largest to the right. Another straightforward approach to sorting is insertion sort. Rather than searching through all the elements, this approach begins by examining the first two elements in a list. The smaller of the two is then moved to the front. This is repeated for every element, each one being compared to the element on its left. A subsequent switch to the left is made if it's found to be smaller. So, element 2 is compared with element 4. It's found to be smaller, so a swap happens. Next, element 2 is compared with element 1. It's found to be larger, so no more comparisons are made. Then, element 3 is first compared with element 4. It's found to be smaller, so a swap occurs. Next, element 3 is compared to element 2. It's larger, so no further comparisons are made. Let's explore an example of this. On screen, you'll notice an array of numbers. The first element, 35, has nothing larger to the left, so it remains where it is. Then, element 46 is compared and is also left where it is. Next, you see element 36. This is compared with location 1. It's smaller than 46, so they are swapped. Checks against location 0 shows that no further swaps need occur for this element. At step 3, you'll notice element 9. This is compared with 46 and is therefore swapped to location 2. It is further compared with location 0 and 1 and swapped again. Next, the element found at location 4 is compared with location 3 and swapped. It's further swapped with location 2 and location 1. It's also compared with location 0, but as it's greater, no further movement is made. The process is continued, moving from right to left until the entire array is sorted. Both the insertion and selection sort are straightforward approaches working on a simple paradigm. Quicksort is a more sophisticated approach that is more complex to implement. However, it shows far greater efficiency. Quicksort operates on the principle of pivots. The algorithm selects an element in the array as the pivot. Then, all items in the array larger than this value are moved to the right of the pivot, and all elements less than the value are moved to the left. This process is repeated for both sides of the pivot until all the items are sorted. Let's explore this in an example. Here, element 9 is selected as the pivot point. Using quicksort, all items that are less than 9 are swapped left, and all items larger than 9 are swapped right. Therefore, the smaller elements have now been moved left after this first split. In this example, these smaller elements are 6 and 3. Applying the same procedure again to the resulting array terminates when 3 is found to be the only element not split. Now, taking the values that are greater than the original selected pivot, you select a new pivot. In this case, 36 is selected and a further swapping of elements is performed. Finally, the remaining unsorted index locations are swapped in relation to a new pivot. Once all elements have been sorted, the algorithm terminates. There are many additional sorting approaches that can be used, with some approaches even forming hybrids of these existing ones. In practice, you probably would not write your own implementations, as there are excellent implementations in every language. The goal here is to show how they operate under the hood, so that you can choose the best one when faced with a given problem. As with data structures, there is not one sorting algorithm that provides the best result in every given scenario. Each approach has its trade-offs and is more effective in some environments than others. You will learn more about the efficiency of these approaches when compared to Big O notation soon. In this video, you've explored sorting algorithms and the different sorting methods that are available to you. You have also learned about the steps required for implementing selection, insertion, and quicksort, and discovered the strengths and weaknesses of each sorting approach. In the previous video, you explored sorting and were introduced to several sorting approaches that can be used for a data set. However, what if you need to search this data for a specific element? In this video, you'll be introduced to some of the various approaches to searching, such as linear and binary. You'll also discover the steps involved in implementing both of these approaches and explore the advantages they offer. In computer science, searching is a fundamental operation. When provided with a collection of data, there may be a need to identify specific elements within this data. However, the exact description of the element does leave room for some interpretation. From the onset, you might consider the question: given a hash table, is there a key value pair that matches this key? This is a simple like-for-like comparison that will produce either the absence of a unique key or the return of a unique key. Some considerations when making a search might include finding the largest number in this array, or the smallest, or to return the median number from this collection of numbers. However, what if the value does not exist? What should be returned? Returning a null value can interfere with an application's ability to run afterwards. When doing a search, you need to consider what safeguards should be put in place when there is no value returned. You should also consider if the search is supposed to return the first instance of the value or the last. In the additional reading at the end of this lesson, there is a link to a talk from Tony Hoare, the inventor of null, who refers to it as his billion-dollar mistake. The simplest search that you can implement is a linear search. If you have an array of elements, a linear search begins at the start of the index and searches through the array until an appropriate element is found, or there are no more elements to check. In this approach, the best case scenario would be O of 1, and worst case, O of n, as each element would have to be checked before it's possible to say that the target element is absent. In relation to data structures, it has been shown that some have inherent sorting tendencies, such as a heap or a binary tree. You can also take any data structure and apply a sorting algorithm to it before applying a searching approach. Using a binary search will halve the search space at each iteration. On screen is a data list. A binary search will firstly check the halfway point and determines if the element is greater or smaller than the target element. If the middle element is less, then the left half of the list is discarded and the right half becomes the focus. So, now only the right half of the list is queried for the middle value. Again, if it's less than the target element, it is once again discarded, and the right half of that filtered list will be examined. In this way, the algorithm halves the search space at each iteration. This approach is quicker than a linear search, but does require the data to be sorted before beginning the search. It may not seem like a reasonable requirement to have this, but if your data is read more often than it is updated, then such a solution might be an appropriate implementation. Again, as with the linear search you covered earlier, the best possible outcome from this approach is that the element is found in the first go O of 1. However, the worst case scenario is less optimistic. After the first search, the list is halved. If this iteration is not successful, it is halved again. Then after the third division, it is halved again, and so on. Therefore, it can be said that after j iterations, it is n over 2 to the power of k, or in other words, O log n. This is considerably more efficient than a linear approach. However, it is worth bearing in mind that any perceived gain in time needs to be offset by the time taken to sort the list. If the list is updated regularly, this can become a costly process. In this video, you explored binary and linear search functions, the steps taken to complete these searches and how they work. You also learned how the application of Big O can be used to estimate the efficiency of both. You've even learned how through some clever adaptations to a standard approach, it's possible to seriously improve performance. Keep up the great work. In the next lesson, you'll start learning how to work with algorithms. The divide and conquer paradigm offers a useful framework for thinking about how to solve a given problem. It encompasses two principles discussed in this module, namely recursion and breaking problems down into smaller problems. In this video, you will learn about the divide and conquer paradigm and how it offers a framework for problem solving. You will also learn about the mandatory and optional steps involved in the divide and conquer paradigm and what advantages this paradigm brings to computers. So how does the divide and conquer algorithm work? The algorithm comprises two steps with an optional third, namely divide and conquer, which are the mandatory steps, and combine, which is an optional step. In the divide step, the input is split into smaller segments and processed individually. In the conquer step, every task associated with a given segment is solved. The optional last step, combine, is combining all the solved segments. This will not happen in every instance, but will for the example provided. The following is an example of the divide and conquer paradigm. When discussing sorting approaches, it was shown that there are many ways to solve a problem. Using sorting as our example, let's discuss another sorting approach that can be solved using a divide and conquer approach. Merge sort is a sophisticated approach for sorting an array. It starts by halving the array. These two halves are then halved and halved again. This process is repeated until there is only one element remaining. Then the process reverses and each smaller list is sorted before rejoining the part it was halved from. This solution to a problem is based on the idea that by breaking a problem into smaller problems, it is easier to complete the overall task. To gain greater intuition on how divide and conquer can be applied to merge sort, let us explore a real-world example. Consider you and three housemates have decided to do the shopping together. After having compiled an extensive list, you all go to the supermarket. One solution might be that you all walk around the supermarket and pick up each item from the list. A better approach might be to break the list into 4 parts and each take a section. This would reduce the overall time spent in the shop. Though this might cause an amount of overlap between parties, a further optimization of the task then might be to first sort the list so that all similar items are together. For example, all the beverages, the fruits, the meats, and so on. Then, assign each member a given area of the supermarket. This would be an even more efficient approach to completing the task. They say a problem shared is a problem halved. So how does this work on computers? There are two immediate advantages, namely parallelization and memory management. Parallelism is when you have different threads or computers working on the same problem at the same time to complete it in a quicker time. A benefit to employing divide and conquer solutions is that you can then employ parallelism when coding. Now, let's explore memory management. With the merge sort example, consider that each array can be sent to a different core or server depending on the architecture of your organization, and the results are then returned. It might be that the data being processed is too large to hold in memory and must be processed in chunks. Additionally, the boss may have provisioned access to cloud computing, so the solution can involve accessing an online server and exporting some of the problems from the company servers. All this contributes to managing your available memory. In this video, you were introduced to the paradigm of divide and conquer through an example of merge sort and how it offers a framework for problem solving. Some various terminology associated with it, as well as how this approach lends itself to real-world computer optimization approaches, were demonstrated. You also learned about the mandatory and optional steps involved in the divide and conquer paradigm, and what advantages this paradigm brings to computers. In a previous video, you learned about the divide and conquer paradigm. In this video, you are going to learn about recursions and how to implement the requirements for a recursive solution. One of the basic tenets of any given language is its ability to perform loops. Loops enable us to perform actions repeatedly until the desired output is achieved. Unlike humans, computers never tire of performing the same mundane task repeatedly. An alternative approach to solving a problem than a loop is recursion. The practice of having functions call themselves is referred to as recursion and the focus of this video. Recursion is when a function calls itself with a smaller instance of a problem repeatedly until some exit condition is met. So what is required for recursion? There are three requirements for implementing a recursive solution, namely the base case, the diminishing structure, and the recursive call. Let's look at an example relating to binary to better illustrate these three requirements. Consider a challenge where you are tasked with finding the exponent of a number. Recall that calculating an exponent of a number is to determine how many potential permutations can be derived from it. This was discussed when demonstrating how binary can be used to represent a range of characters. The base case ensures that the function will not continue to call itself and eventually ends. Line 1 outlines a function that will take two arguments, x and n. The base case is if n equals 0. In this instance, the program will terminate. Line 4 is the second part of the conditional statement. If a termination point has not been reached, call the function again with a reduced structure. In this instance, the goal is to multiply x by n to find the total number of potential states that could exist for the binary number. Reducing the input value is as important as establishing a base case. This way, the function will eventually reach the base case and cease to call itself. The third component of a recursive function is to include a call to itself. This happens on line 5, where the exponent is accepting the diminished structure. The structure can be said to be diminished because the size has been reduced from one call to another. Each time the function is called, a new instance is created on the call stack. Calling the above function with x equals 2 and n equals 3 will result in 3 instances being created and placed on the call stack. This increases computational cost as resources are required to make a function call. However, the computation from each result will be retained on the call stack. This can be useful when computing hierarchical problems or problems where one can benefit from knowing which steps resulted in a given outcome, like traversing a graph. Let's explore an example of the use of recursion. Consider the video on binary search. A binary search function will accept an argument of a list and a target value. First, the middle point of the list is checked against the elements to determine which half of the list to check. This process is repeated until the target element is found or deemed to be not there. You might consider solving this problem through a loop or recursively. The input to the recursion would be a list and a search element, and the recursive function would call itself until the target endpoint is reached. So why then use recursion when a simple loop will do? some problems lend themselves well to recursive calls. Consider calculating the Fibonacci of a given number. Fibonacci is a sequence of numbers where the first two numbers are 0 and 1, and every other number is the sum of the previous two numbers in the set. Calculating the result involves passing a number, calculating the output, changing the number, then calling the function again with a new integer input. Writing the code this way means that you can simply call the function with a different integer, and it will return a breakdown of the required steps. Readability is a strong plus for recursion. Sometimes when a problem requires many checks, a loop can quickly become unwieldy. Recursive solutions reduce the amount of code required to solve a problem and can be easier to read and understand. Finally, one would employ a recursive approach as part of a divide and conquer solution. Here, the problem is broken into smaller steps and repeated to come upon the optimum solution. In this video, recursion has been introduced. You have learned that while recursion can add some computation overheads to a problem, it can also result in eloquent, easily read code. Additionally, that recursion epitomizes a divide and conquer solution, breaking the problem into its smallest components and solving those. In the build-up to dynamic programming, you have learned about the divide and conquer paradigm and recursions. In this video, you will learn about the concepts of memoization and dynamic programming. Dynamic programming is a programming paradigm that promotes solving problems by breaking them into smaller problems and solving these. The solutions are then stored in an appropriate data structure for later use. The advantage to this is that if these subproblems require being computed again, one only searches for the answer instead of computing the problem again. The technique of solving subproblems and storing them to save time on a potential future lookup is known as memoization. Dynamic programming relates to two concepts already encountered in the previous videos. Let's have a quick refresher on these concepts. The first is divide and conquer. That is, taking one large problem and breaking it into a smaller set of subproblems and then solving these. The second is a subset of this, known as recursion. Recursion is the practice of coding a solution that avoids running loops, but instead uses multiple self-calls in coming upon a solution. Dynamic programming is an extension of these approaches, which in addition involves keeping a record of results generated from running the subproblems each time they are newly run. In subsequent runs, instead of recomputing results, a lookup is queried for the last time the question was asked. As said, this approach is called memoization. And to reinforce the concept, this is when the results of previous calculations are stored and used in place of rerunning the calculations when the compiler identifies that the computation has been run for a previous task. To exemplify this, consider the question posed in the video about binary numbers. How many combinations were possible with a binary lock of 6 digits? In a previous video, it was shown that you can discover this through exponentiation or finding the power of a number. So the same lock with 6 digits would have 2 to the power of 6 or 64 combinations. So 2 to the power of 6 equals 2 times 2 times 2 times 2 times 2. Alternatively, you can divide these into two groups where you have calculated 2 times 2 times 2 and again 2 times 2 times 2. That will result in 8 times 8 and again give the same result. Applying a divide and conquer approach to computing this efficiently using memoization would reduce the computations by first calculating to the power of 3 and again 2 to the power of 3. By applying memoization, the first 2 to the power of 3 would be computed, then reused for the second bracket, reducing the overall computation required. So, what sorts of problems are good fits for a dynamic solution? The dynamic programming approach is commonly applied to combination or optimization problems. One example of a combination problem already mentioned is the Fibonacci sequence. Another instance you may encounter in an interview is the knapsack problem. This is both a combination and an optimization problem. Say for a planned camping trip, you can fill a knapsack with required items. Each item has a weight cost to it. A torch equals 1 kilogram, water equals 2 kilograms, and the tent equals 3 kilograms. Additionally, each item has a value. The torch equals 1, water equals 2, and the tent equals 3. In short, the knapsack problem outlines a list of items that weigh different amounts and have different values. You can only carry so many items in your knapsack. The problem requires calculating the optimum combination of items you can carry if your backpack can carry a certain weight. The goal is to find the best return for the weight capacity of the knapsack. To compute a solution for this problem, you must select all items that add up to a given weight and contain a given value. The weight carryable will change. This problem can be applied to resource allocation, where you have so much CPU power and X tasks to run, just like the capacity of a CPU dedicated to completing tasks. Sometimes the weight will be 7 kg, and other times it might be 10 kg. Dynamic programming involves saving the computations used to come upon a given solution. So, if you have computed an optimum selection for 7 kg and it is raised to 10 kg, you will not have to rerun the initial computations again. This can be a time-saving metric. When computing dynamic programming solutions, you must firstly determine the objective function. That is the description of what the optimum outcome is to be. Next, you must break the problem into smaller steps. One approach already discussed for achieving this can be the use of recursive functions. That is, functions that will call themselves repeatedly until a solution is come upon. They should be written in such a way that you can change the outcome without altering the code for the methods already written. To conclude, in this video, it has been shown that dynamic programming is an approach that looks to optimize solutions to a given problem. It uses principles of memoization and overlapping subproblems to identify when an objective function can be achieved quickly, optimizing the computation steps required. In this video, you will learn how you can implement this paradigm to solve complex problems by using greedy algorithms. There is a philosophical principle called Occam's razor. It states that the simplest solution is almost always the best one. This problem-solving principle argues that simplicity is better than complexity. In our case, the greedy algorithm is the simple solution. This is an alternative approach to dynamic programming, as this approach seeks to present an immediate solution for a task and favors local optimization over a more holistic global approach. When engaging with a problem subdivided into segments, utilizing a dynamic programming approach would find a globally optimal solution so that each subproblem is solved and the best subset is selected and implemented. A greedy approach would instead look at the list of solutions and implement a local optimization. Usually, the current most rewarding option is chosen. To make this more clear, let's take an instance of a CPU that has a list of tasks to be completed. Applying the dynamic programming approach would entail selecting a subset of activities that could be completed within a given time and executing these tasks. With the knapsack analogy, this would involve determining what subset of items to pack that would maximize the value in the process of filling the bag. A greedy algorithm approach to this would be always to select the most valuable item and place this in the bag, giving no thought to what other items this would exclude from the process. Thus, in our CPU example, a greedy approach would involve selecting first the shortest running program and then the next shortest program, and so on. While this might not lead to a globally optimized solution, it will reduce any overhead in calculating the most efficient subset of items. To better understand how these two approaches would differ, let us consider the problem of the shortest path. The image shows a map with 9 different nodes: A, B, C, D, E, F, G, H, and S. Each node is connected to another node by a weighted path. This weight reflects the cost that would be incurred by selecting this path. Thus, in our CPU example, a greedy approach would involve selecting first the shortest running program and then the next shortest program, and so on. While this might not lead to a globally optimized solution, it will reduce any overhead in calculating the most efficient subset of items. You are now faced with making a journey from E to F and want to plot the most effective route. A dynamic programming approach would involve creating a table and calculating each potential node from E. From there, it would introduce the next set of nodes and calculate the accumulated cost. This approach would undoubtedly arrive at the most efficient solution. Using memoization, after the initial calculations were made, they would be saved, and subsequent journeys would benefit from a quicker computed time. This is a bottom-up global approach to the problem. A greedy approach would differ in its methodology. Instead of trying to find an optimal subset of connected routes, it would instead begin at node E and look at each available connection. Thus, it would have a selection of weights, namely 5, 3, 2, 4, and 12, which correspond to nodes C, B, D, G, and H. The lowest value in that array is 2, which corresponds to node D. Following the greedy principle, it would make this selection and progress to the next node. Assuming that the data structure was a directed graph, it would be presented with a further 3 nodes, A, F, and G, that have the values of 7, 5, and 6 respectively. Since F is the final location, it would select F and arrive at its destination happily, having amassed a total penalty of 7 for travel time from E to D and then to F. That carries a weight of 2 plus 5. Visually, you can see that this is the most efficient approach, and it was come upon without creating an exhaustive table of combinations and computing all routes. However, had the node between G and F had a penalty of 2, then it would have selected a less optimal solution. This is the trade-off when choosing a greedy approach over a dynamic one. While the overhead for a greedy algorithm is low and coding a solution is quite straightforward, it will not always guarantee that the best option is returned. You now have a greater understanding of the greedy algorithm approach. In addition, you have seen how it compares with a dynamic solution and thus deepened your grasp of the strengths and weaknesses of this alternative approach. Next time you are plotting a route in Google Maps, consider the selection of routes that are offered and think about how these routes might have been calculated. Well done! You've reached the end of the Working with Algorithms module. Let's take a few moments to review what you learned during this module. You began the module with a lesson on sorting and searching. First, you learned about why sorting is important and explored the 3 main methods for sorting: selection, insertion, and quicksort, and examined the steps involved for each method that these algorithms use to sort data, and explored the strengths and weaknesses of the 3 sorting approaches when choosing an algorithm to use for a given solution. Importantly, that there is not one sorting algorithm that provides the best results in every given scenario. Next, you learned about searching algorithms, which are a fundamental concept in computer science, and some of the various methods that are used by algorithms for searching. You explored 2 core approaches to searching: linear and binary. Linear searches progress through every item in a given data structure until a specific item is found, whereas binary searches half the search space at each iteration. You also learned the steps involved in implementing both approaches and some of the advantages they offer. You also took a deep dive into time and space complexity for both searching and sorting algorithms. You then moved on to the next lesson, where you were introduced to working with algorithms. Here you learned about different approaches to working with algorithms. First, you explored the divide and conquer paradigm. In the divide step, the input is split into smaller segments and processed individually. In the conquer step, every task associated with a given segment is solved. And the optional last step, combine, is combining all the solved segments. And you discovered how the divide and conquer technique offers an effective framework for problem solving and the various benefits that it provides. Next, you explored another important algorithmic approach, recursion. Recursion is when a function calls itself with a smaller instance of a problem repeatedly until some exit condition is met. And you learned that there are 3 requirements for implementing a recursive solution, namely the base case, the diminishing structure, and the recursive call. You were then introduced to dynamic programming, which is a programming paradigm that promotes solving problems by breaking them into smaller problems. You explored the concept of memoization, the technique of solving subproblems and storing them to save time on a potential future search. And you examined the process involved to compute a dynamic programming solution. Essentially, this can be outlined as first, determining the objective function. That is the description of what the optimum outcome is to be. Next, breaking the problem into smaller steps, and then deciding which dynamic programming approach you would like to apply to achieve your desired outcome. Finally, you learned about greedy algorithms. In comparison to the dynamic programming approach, a greedy approach would look at the list of solutions and implement a local optimization. Usually, the current most rewarding option is chosen. You explored how a greedy algorithm approach could be implemented to reach a solution, and that there is a trade-off when choosing a greedy approach over a dynamic one. While the overhead for a greedy algorithm is low and coding a solution is quite straightforward, it will not always guarantee that the best option is returned. With all the knowledge you have acquired, all that is left is to complete the final quiz for this module before moving on to the final module, where you will complete the graded assessment. And then you've really made it. You're so close. Good luck and enjoy the rest of your journey. In this course, you have learned a range of concepts and skills as you prepare for a coding interview. Let's take a few moments to recap the key topics that you learned about. In the first module, you started by discovering what a coding interview is, what it can consist of, and the types of coding interview that you might encounter. Your first lesson focused on the technical coding interview, primarily to determine that you are technically capable of the role's responsibilities. You learned about the steps that you must keep in mind when this interview is conducted. You were taught that using the appropriate tools is always important and that you have to keep time constraints in mind. You also explored how you can prepare yourself for a coding interview and the importance of first impressions, including a focus on communication, such as explaining your thought processes and handling mistakes. You learned about the STAR method and how to use it to your benefit when communicating with interviewers. You also learned about how to work with pseudocode to demonstrate how you might reach a solution, some important tips for practical solution design, and how to test your solutions. In the next lesson, you got an introduction to computer science, starting with an overview of binary, where you learned about the difference between base 10 and base 2. You then discovered positional notation, the use of the position of the number to denote a progressive increase in value. You then moved on to explore key components of computer memory and how it works. You should know by now that to better understand the various layers of memory and should be able to describe the differences. You learned about the transfer rate, or the speed at which a computer can transfer memory into the cache for processing. You then moved on to time complexity, where you learned how to evaluate time efficiency, or gauge performance by the time taken to complete a task. You discovered Big O notation, which is a metric for determining an algorithm's efficiency. You explored space complexity, which is essentially the space required to compute a result, and that any decisions around space complexity are not just based on the speed of an algorithm, but also on how much memory capacity a given solution will use. There will always be a choice to prioritize speed or compactness. In the second module, you learned about data structures. This ranged from basic data structures like strings, booleans, or arrays to more advanced data structures like collections, graphs, and heaps, and how each one comes with certain benefits and limitations. You explored all the types of data structures and how they are classified into two main branches, linear and nonlinear. Next, you were introduced to stacks and queues, abstract data structures that both have specific characteristics around how elements are added and removed. When you visited queues, you learned that a queue is very similar to a stack in that it tends to have the same methods. It can create, insert, remove, and check the state of the queue. Unlike a stack, a queue works on a first in, first out, or FIFO basis. Finally, you found out that trees are a powerful data structure that give you great flexibility in adding and searching values. Following this, you went on to examine some advanced data structures, namely hash tables, heaps, and graphs. Next, you explored heaps. You discovered how heaps can be used to organize elements from least to most important, and how, by limiting the functionality of heaps, productivity can be increased. Finally, you examined graphs. This structure illustration is a graph that is made up of nodes to denote destinations and edges that show how each node relates to another. The presence of values between the nodes mean that this is a weighted graph. There are no arrows present, which means that it is an undirected graph. In contrast to a directed graph, an undirected graph has no order of precedence. And you learned that a connection in a directed graph is considered weakly connected if the edge is only one way. However, if there are two connections going either way between two nodes, then it is said to be strongly connected. In the third module, you had an introduction to algorithms, including the types of algorithms available to you and how best to work with them to sort and search your data. You started by exploring sorting algorithms and how working with sorted data or having the ability to sort your own data can result in significant time savings. You discovered why sorting is important and explored the three main methods for sorting: selection, insertion, and quicksort. Next, you went on to discover searching algorithms and how each type provides its own framework for problem solving. You explored two core approaches to searching: linear and binary. Linear searches progress through every item in a given data structure until a specific item is found, whereas binary searches half the search space at each iteration. You also gained insight into time and space complexity in both searching and sorting algorithms. You then moved on to the final lesson, where you were introduced to working with algorithms. Here you learned about different approaches to working with algorithms. First, you explored the divide and conquer paradigm. You learned that in the divide step, the input is split into smaller segments and processed individually. In the conquer step, every task associated with a given segment is solved. And the optional last step, combine, is combining all the solved segments. Next, you explored another important algorithmic approach: recursion. Recursion is when a function calls itself with a smaller instance of a problem repeatedly until some exit condition is met. And you learned that there are three requirements for implementing a recursive solution, namely the base case, the diminishing structure, and the recursive call. You were then introduced to dynamic programming, which is a programming paradigm that promotes solving problems by breaking them into smaller problems. And you examined the process involved to compute a dynamic programming solution. Essentially, this can be outlined as first determining the objective function, That is the description of what the optimum outcome is to be. Next, breaking the problem into smaller steps and then deciding which approach you would like to apply to achieve your desired outcome. Finally, you learned about greedy algorithms. In comparison to the dynamic programming approach, a greedy approach would look at the list of solutions and implement a local optimization. Usually, the current most rewarding option is chosen, and you looked at an example of how a greedy algorithm approach could be implemented to reach a solution. While the overhead for a greedy algorithm is low and coding a solution is quite straightforward, it will not always guarantee that the best option is returned. So, there is a trade-off when choosing a greedy approach over a dynamic one. Well done! You have covered so many important concepts and approaches throughout this course. It is a real achievement, but it should also serve to prepare you for any potential coding interviews that you may go on to attend. All you have left to do is to take the final course quiz before wrapping up the course. Good luck. You've reached the end of this coding interview preparation course. You've worked hard to get here and accumulated a lot of knowledge along the way. You've made great progress on your developer journey. You should now understand the unique and challenging aspects of the coding interview. Specifically, you should be well prepared with some interview soft skills that will help you to be ready when you go for your coding interview, the foundations of computer science, and some problem-solving methods to apply to any challenge you may face in an interview scenario. Following your completion of this course in coding interview prep, you should now be able to prepare for the interview process, offer strategy and tips for successful interviewing, and openly discuss the emotional components of the process. The key skills measured in the graded assessment revealed your knowledge and understanding of data structures in the context of coding interviews, the concepts and usage of algorithms, how to visualize an algorithm, and combining new and previously learned coding patterns to solve problems. Congratulations! You've successfully completed all of the courses in this program. At this stage, you may want to consider registering for another course, specialization, or certificate pathway. Certifications provide globally recognized and industry-endorsed evidence of mastering technical skills. Whether you're just starting out as a technical professional, a student, or a business user, the courses you have completed and the range of practical projects you have in your portfolio will prove your knowledge and ability as a developer. These can serve to demonstrate your skills to potential employers, and not only does it show employers that you are self-driven and innovative, but it also speaks volumes about you as an individual, as well as your newly obtained knowledge. You've done a great job so far, and you should be proud of your progress. The experience you gained so far will show potential employers that you are motivated, capable, and not afraid to learn new things. Again, congratulations on finishing this course, and good luck with the rest of your educational journey.